everybody. Welcome to Chapter 8 on hypothesis testing, where we'll be covering Section 8.2, Basics of Hypothesis Testing. So the key concept in this section is we're going to talk about different components of a hypothesis test. And we're going to learn some different things about this. So first things first, we're going to learn how to identify the null hypothesis and the alternative hypothesis from a given claim and how to express both of them. We're going to calculate the value of a test statistic, and then, basically that will be based on a given claim and the data that were provided. We're going to learn how to choose which sampling distribution is relevant to the different problems. We're going to learn how to identify a p-value or identify critical values. As you'll see, there's two different ways to do that. And then we're going to learn how to state the conclusion about a claim in simple, very non-technical terms. So this is a bit of a long section, so bear with me as we're going through. But nonetheless, these will be all the topics that we're going to cover. So some definitions to start. A hypothesis is a claim or statement about a property of a population. So hypotheses are made about populations. And a hypothesis test is a procedure that tests the claim about that property of a population. So in both of these cases, we're going to make a hypothesis, and then we're going to have a test to actually prove whether that claim is true or false about whatever property we happen to be looking at. So we've talked about rare event rule earlier in the course, but a couple of things just to remind you of. Basically, if the probability of a particular event is very, very small, then we're going to assume that whatever assumptions we made about that event were not correct. So let me give you an example of this. So say, for example, that we flip a coin 100 times. And we assume for the purposes of this coin flip that the coin that we're using is a fair coin, meaning it should have around a 50-50 chance of landing on heads or tails. And when we perform our procedure and we flip the coin 100 times, we observe that 99 out of the 100 times we got tails. Well, we know that the proportion should be around 50-50 for heads and tails. So we would actually have to conclude that if we received 99 out of 100 times tails, that our original assumption that the coin was fair was probably incorrect. So that would be what rare event rule tells us, is that if something seems too good to be true, it probably is. Okay, let's keep going. So in hypothesis testing, we're going to have a null hypothesis and an alternative hypothesis. And it's important that we define what each of those is and that we know how to state them in terms of symbols. So the null hypothesis is denoted by this H kind of sub-zero. So an H with like kind of a zero as a subscript. And the null hypothesis is a statement that the value of the population parameter, and a parameter could be something like a proportion, a mean, a standard deviation, that it's equal to some claimed value. So the null will always be equal to something. And we're going to test the null hypothesis directly in the sense that we're going to assume that it's true. And once we actually do out our test, we will either reach the conclusion that we either need to reject the null, meaning that the null is not true, or we're going to fail to reject the null, which means that it will be true. In contrast with that will be our alternative hypothesis. The alternative hypothesis is denoted by an H with a subscript of 1 or an H with a subscript of A. I typically see this one used more frequently, H sub A. And that's the statement that the parameter has a value that differs from the null hypothesis. So if our null hypothesis is that that the parameter is equal to some claimed value, the alternative would be that it's higher, lower than, or equal to, or not equal to whatever your null is. And this will make more sense once we get into an example. It's a little bit abstract right now. Okay, so some things about forming your own claims. If you're conducting a study and want to use a hypothesis to support your claim, the claim has to be worded so that it becomes your alternative hypothesis. So this again will make a little more sense once we do an example, but basically the claim will always be worded the same way that your alternative hypothesis will be worded. Whereas your null will always be not how your claim is worded. So some steps. These are steps 1, 2, and 3 of how you identify your null and your alternative hypothesis. So we're going to identify the claim or the hypothesis we want to be tested, and we're going to put it into symbolic form. We're going to give the symbolic form that must be true when the original claim is false, which would be basically that would be our null. And then of the two symbolic expressions, we're going to let our alternative hypothesis be the one not containing equality. So basically our alternative is going to either have a greater than symbol, a less than symbol, or a not equals to symbol, where our null hypothesis will be equal to some fixed value that we're considering. Okay, so here's an example. So we're going to assume that 100 babies are born to 100 couples treated with the X-sort method of gender selection that is claimed to make girls more likely. So this method basically is for people undergoing, I believe, in vitro, where they take eggs and they sort them in a way that is supposed to be able to make you have a higher likelihood of girls being born. So we observed that 58 girls and 100 babies were born with this method. And we're going to write our hypothesis to test the claim that with the X-sort method, the proportion of girls is greater than the 50% that occurs without any treatment. Okay, so first things first, let's define our null hypothesis, because it's actually usually easier to start there. So our null in this case is going to be what is stated in our claim, that the proportion of girls is greater than 50% that occurs without any treatment. So our P in this case is going to be greater than 50%, which is 0.5 when you turn it into a percentage. And our null in this case is going to be that our P, or our proportion in this case, does equal that 50%. So 50%, if you think about it this way, at 50%, that would have a 50-50 split of boys and girls, which is what we expect to see. Whereas our alternative is that this method actually increases the likelihood of girls. So that in this case, our proportion of girls would be greater than 50%. So here's how how we've defined our null. Our P is equal to 50% or 0.5. And our alternative is that our p-value is greater than 50% or 0.5. Okay, so once you have defined your null and alternative hypothesis, it's time to select a significance level. And if we think back to what we learned in Chapter 7, these are going to be very similar. So with significance level, it's very similar to what we saw in Chapter 7. And I want to see what they share here. So they kind of give you this little warning here, but the real important thing that I want you to pay attention to is what those significance values are. And again, they're the same as what was introduced in Section 7.2. They're 0.05, which would correspond to 95% confidence level, as we saw in Chapter 7. 0.1, which would be a 99% confidence level. And 0.1, which would be a 90% confidence level. And these values that you get, the difference between your confidence value and subtracting that from 100 is that significance level. And so our common choices are going to be the exact same thing that we saw in Chapter 7, 0.05, 0.01, and 0.1. Okay, so once we have determined our significance level, it's important to identify what test statistic we're going to use and what sampling distribution we have. Now, depending on what parameter we're looking at, and you'll use a different test statistic. So if the statistic that you're after, if you're looking at a population proportion, you'll use this z-score test statistic. If you're looking for a mean, you'll use this t-score statistic. So these are similar to what we saw in chapter 7. If you're looking for a mean, now this would be if you were using a t-distribution. This would be if you were using a z-distribution. So this would be your test statistic. And if you were doing standard deviation or variance, you would use this one, although we haven't talked about that one at all. The only ones that we've really seen in Chapter 7 were proportions, which we covered in 7.2, and means, both using a t-score and a z-score, which we covered in 7.3. So once you determine which parameter you're looking at, you'll use the corresponding test statistic for your later calculations, as we'll see. Okay, so this test statistic is the value that we're going to actually use in making our decision about whether the null hypothesis is true or not. And we're going to basically convert our sample statistics into one of these test statistics. And we're going to assume that the null hypothesis is true when we do that. Okay, once we find what test statistic we're going to use, we are going to then use that test statistic, or I should say that relevant sample statistic, to standardize it into that test statistic. And then from there, we're going to use that test statistic to help us find either a p-value or a critical value. And we'll talk through what that means in a couple of minutes. I know this is a little abstract until we get to an example. So here is an example, and hopefully it'll shed some light on what we just covered. So we're going to go again back to that same example of the XSORT method of gender selection increasing the likelihood of having a baby girl. The preliminary results from the test involved 100 couples who gave birth to 58 girls and 42 boys. We're going to use this claim that XSORT increases the likelihood of having a baby girl, and the preliminary results that were reported here to calculate the value of the test statistic. And then we're going to use that test statistic, we're going to use that test statistic basically to approximate our distribution. And from there, we will select whether we're going to have a p-value or a critical value. So let's jump into this. So we saw, just like we saw when we were originally looking at this example, we had defined a null hypothesis of that our p, which in this case is a population or a population proportion, is equal to 50%, meaning that you'd have a 50-50 chance of having a boy or a girl. And then we defined our alternative hypothesis is that our p-value, our sample proportion, would be or our population proportion, I should say, would be greater than 50%. So we're going to work under the assumption that the null hypothesis is true, with p equaling that 50%. And then we're going to compare to that our sample proportion, in which case we had 58 girls and 100 births, which would give us a sample proportion. So if this is our population proportion is 0.5, our sample proportion, based on the data that we were provided in this example, would be 0.58. So this is our population proportion assumption, and this is the actual sample proportion that we were able to calculate using the data that was provided in the problem. So from there, we would use this z-score statistic. So let's take a look at why that is. So let's go back to this. So we have a population proportion, a p-value. So we're going to use this test statistic, which is going to give us a z-score, where we're going to have our sample proportion minus our population proportion divided by the square root of p plus q, or p times q, divided by n. So let's go back, and we're going to do this calculation for our example. So here we go. So we found our p-hat, or our sample proportion, to be 0.58, and that our population proportion was 0.5. Remember, we're going to assume that the null is true. Then we're going to divide that by our population proportion of p, which is 0.5. 0.5, 1 minus 0.5, which is how we calculate our Q, is also 0.5. And then divide that by 100, which was the number of people that we had. And when we do that, we find we get a z-score of 1.6. And we know from previous chapters that, and this is from range rule of thumb, that anything within 2 standard deviations, or having a z-score of less than 2, is not unusual. So in this case, it would seem that this method does not necessarily support the claim that the method increases the likelihood of having a girl, because 58 girls out of 100 births is considered usual, meaning that that would not tell us that something unusual had happened, such as using a method that increased the likelihood of having a girl. So that would be, so we took this example through defining our null and our alternative, calculating our sample proportion, and finding our test statistic and determining whether that test statistic was normal or not normal based on what we know about z-scores. Okay, so now that we've covered all of that, we need to talk about different types of hypothesis testing. So in hypothesis testing, you can have a two-tailed test, a left-tailed test, or a right-tailed test. And I'm going to show you what those things mean, but basically the tails in a distribution are the extreme regions, and there's a critical value, usually a z-score, that's going to separate those tails. And those tails, those critical values, separate the values that are considered usual from the values that are considered unusual. And so it's important that we understand whether a test is two-tailed, left-tailed, or right-tailed. So let me show you what I mean by that. So this would be a two-tailed test. So in this case, our null would be equal to something, and our alternative would be not equal to something. And that critical value would be basically split into two different regions. So you'd have a region up here and a region down here. And so don't let this confuse you. Think about the bell-shaped curves that we saw in chapters 6 and 7. So in here, imagine like our range rule of thumb that we covered several times. You'd have a mean, and you could go out 2 or 3 standard deviation from the mean, 2 or 3 standard deviation from the mean, and that's going to be where your usual values fall. And anything that's outside of there would be your unusual values. Now in this case, our fail to reject our null, meaning our null is true or could be true, would be in the middle, and anything that is an alternative would be in one of the tails, meaning that you have to reject the null, that something else is happening. So that's a two-tailed test. A left-tailed test is the same, except all of the critical value here is separating, basically it's all on one side. That everything through here you would fail to reject the null, and that you would only reject the null if it was in the left. And the right is the exact opposite. It's where that critical value is over here, and that everything over here on the right-hand side would be where you would reject your null. So again, you can have a two-tailed test, meaning you're splitting it in half, a left-tailed test, meaning that it's stacked to the left, and a right-tailed test, meaning it's stacked to the right. Okay, so now we need to talk about p-values. So a p-value is also called a probability value, and it's the probability of getting a value of your test statistic that is at least as extreme as the one representing your sample data. And we're going to, again, assume that our null is true. So if you're doing a left-tailed test, your p-value would be the area to the left of your test statistic. For a right-hand test, it would be the area to the right of that test statistic. And for a two-tailed test, it would be twice the area to the tail beyond the test statistic. And you're going to see what this means momentarily. So each, basically you're going to have this p-value. And if that p-value, here, I'll show you. It'll make more sense if we do an example. All right. So within a p-value, there's very clear rules, which is nice. If your p-value is 0.5 or less, you're going to reject your null. And if it's greater than 0.5, you're going to fail to reject your null. So here's an example. So let's follow that same example we were doing before. So here's our XORT method of gender selection. We defined our null as p equaling 0.5 and our alternative being p being greater than 0.5. And we calculated out our test statistic and found that it was 1.6. Okay, so when you look up a z-score of 1.6, it has an area to the right of 0.5. So if you had a right-tailed test with a z-score of 1.6 and a p-value of 0.5, you would fail to reject your null because this is greater than 0.5. Okay, so when you're determining p-values, this is a good diagram to follow. If you know whether you have a left-tailed or right-tailed or a two-tailed test, you can follow this, and this will help you figure out, basically how to define your p-value. So again, this would be a left-tailed test. Here would be your test statistic, or like your z-score or t-score, and your p-value would be this. If your test statistic, if you were doing a two-tailed test, your test statistic would be this boundary, and your p-value would be twice this area, because remember, this is two-tailed, so you'd have to go on either side. For a right-hand test, if your test statistic is to the right of the center in a two-tailed test, it'll be twice this area. And if you have a complete right-tailed test, it'll be this area. So this diagram can actually be really helpful. So I suggest that you guys use this when you're doing your problems to help you. Okay, so now let's talk about critical regions. So the critical region, also known as the rejection region, is the set of all the values of the test statistic that cause us to reject our null, which is basically anything that falls within these red areas that you'd see. And depending on which test you're doing, that red area will fall in a slightly different place, but nonetheless, that is where we reject our null hypothesis. And we also call that, again, our critical region or rejection region. So the critical value is the value that separates the critical region, where we're going to reject our null, from all the values that don't lead to the rejection. So let me come back over here. So basically, this test statistic, what it marks is that critical value. And so over here, this is our rejection region, where we're going to reject our null. And over here is where we would not reject our null. So again, this diagram can be really helpful to help you understand some of the theory that we're going through. So I really recommend using this to your advantage. So again, so the critical value is that value that's going to separate where we're going to reject our null from where we're not going to reject our null. And our critical values depend on the nature of our null hypothesis. And basically, we can have a different significance level. And we talked about significance levels in chapter 7. So we talked about those different, that 0.5, 0.05, 0.01, and 0.1 significance levels. So here's an example. So going back to our same example that we were using, we calculated out for our test group that we had a z of 1.6 and that our sample proportion was 0.58. Now, if we were to use, for example, a critical region of 0.5, we would find that our critical value that corresponds with 0.05, and again, this was the same from chapter 7 that we saw, would be 1.645. And so in this case, our test statistic falls over here. So it's in the region, our test statistic, which is also a z, is in our region where we would not reject our null. Everybody see that? So here's where our test statistic would map. Here's our critical value. So because our test statistic falls within this region, we would not reject our null. Couple things that they caution you here. Don't confuse a p-value with a population proportion. They are different. A p-value is the probability of getting a test statistic that is at least as extreme as one of the ones representing your sample data, where your lowercase p is your population proportion. So just keep those clear because we do have a couple of things now using p's. Okay, so then based on this, we are going to make a decision about whether we're going to reject our null or fail to reject our null. And in this case, there's two different methods. We can either use a p-value method or we can use a critical value method. So let's take a look at those. So for the p-value method, you're going to use whatever significance level you happen to have, which again will vary, but it'll either be 0.05, 0.01, or zero point 0.1. And if the p-value is less than or equal to your significance level, then you're going to reject your null. And if your p-value is greater than your significance level, then you'll fail to reject your null. And when we do the critical value method, if the test statistic falls within our critical region, we're going to reject our null. And if the test statistic does not fall within that critical region, we're going to fail to reject our null, which is what we saw here. This one was based on critical region. So because this value fell outside of our critical region, which is the critical region is over here, we failed to reject our null. All right, so coming back to our example here, using the p-value method, we would fail to reject the null at this significance level, 0.05. And using the critical value method, we would fail to reject the null because our test statistic of 1.6 does not fall within that rejection region. So either way, you should come to the same conclusion. Because again, our p-value that we calculated here was 0.548. And so because that is, again, well, anyway, those are our two methods, our p-value method and our critical value method. Okay, then we're going to restate our decision using simple and non-technical terms. So we're going to state a final conclusion that addresses our original claim with wording that can be understood by anybody without knowledge of what we actually did to determine whether all the statistics behind it. So for example, for the XSORT baby gender test, there was not sufficient evidence to support the claim that the XSORT method is effective in increasing the probability that a baby girl will be born, because we failed to reject our null. Okay, and here's a little diagram that can help you in terms of wording those final conclusions. So, basically you want to be very objective in how you're stating those conclusions. And so some of this is actually helpful. There is sufficient evidence, there is not sufficient evidence, sample data supports it, sample data is not sufficient. That's the kind of wording that people use when they're doing these types of final conclusions based on hypothesis testing. Okay. You never want to conclude a hypothesis test with that you rejected the null or you failed to reject it. You always, and the reason why is because that's a little confusing to people that don't understand statistics. So you always want to make sense of the conclusion with a statement that uses simple, non-technical wording as opposed to using kind of statistics language when you're drawing a conclusion. Okay, couple of things. So accept versus failing to reject. Some texts use accepting the null hypothesis. Now, this text does not do that, and that's because we're not proving the null hypothesis. Fail to reject is more accurate, and that's why they use that in terms of this text. There are a couple of different types of errors that you can make in hypothesis testing. The first one is what's called a type 1 error. A type 1 error is basically the mistake of rejecting the null when it's actually true. And so this is the symbol that's used to kind of designate it. A type 2 error is used when you reject the null when it was, or when you fail to reject the null, but when it was actually false. And they use this beta symbol to represent that type of error. And so there's a couple of things that you have here. So basically you decide to reject the null. Either that was the right decision or it was the wrong decision. If it was the wrong decision, it creates what's called the type 1 error. And if you fail to reject your null, that's either a correct decision or you could create a type 2 error that way. So here's an example. So going back to our XSORT example, We have our null and we have our alternative. So again, our null was that our probability or our proportion was 0.5, and our alternative was that our proportion was greater than 0.5. So we're going to identify a type of type 1 error and a type of type 2 error. So a type 1 error, again, is made where you reject a true null hypothesis. So for example, we would conclude the probability of having a girl is greater than 50%, when in reality it's not. Our data misled us. An example of a type 2 error, again, a type 2 error being where we mistakenly fail to reject our null. This is where there is no evidence to conclude that the probability of having a girl is greater than 50%, meaning our data misled us. But in reality, that probability would be greater than 50%. So those are a couple of examples of a type 1 and a type 2 error. A couple of things that there are things that statisticians do to control these types of errors. And you can read through these, but they're not particularly relevant to what you guys are going to do. But basically, most of the time what it deals around is around sample size. That basically, as you have a larger sample size, you're likely to decrease those types of errors from occurring one way or the other because you'll have a more conclusive answer. Okay. Let's see here. I want to kind of roll through this really quick. The power of a hypothesis test. The power of a hypothesis test is the probability 1 minus beta, which is basically what's covered here in a type 2 error. But I don't want you to spend a lot of time on this, so please don't spend a lot of time on the power of a hypothesis. This is not something that you're going to see much. Okay. And the reason I say this is because for the most part, you're going to be using standards. So I want to walk you through what those are. So just like we saw that when we had significance level, that 0.5, which is 0.05, which is a 95%, or corresponds to a confidence level of 95% was common. You'll also see that a power of at least 0.8 is a very common thing for hypothesis testing. So 0.8 is the commonly used power if you needed to actually define a power. And so, like I said, I don't want you guys to spend a whole lot of time on this, but basically when you design an experiment, a goal of having a power value of at least 0.8 is often helpful when you're trying to determine how big your sample size actually needs to be. But enough about that. All right, that ends section 8.2. And this actually concludes the material that will be covered for Math 120 this semester.